Let's set up our next field cycle. Like before, the system contains two particles of matter. These particles exist in a uniformly expanding field of bosons. Again, we will state that these objects initially exist at rest in relation to one another. Unlike before, however, these objects are separated by a significant distance. This means the energized state of the observed party would not be solely interpreted as a change in velocity. What will we see happen when the primary observer interprets object B's change in momentum as not only a change in velocity but a dilation in mass? We will outline a process that the primary observer can undertake to reconstruct its observed reality. Let's start at time t0. The primary observer A views itself at rest in relation to particle B, and instantaneously, the primary observer observes the scalar field. Reality is fractured. Following the Lorentz transformation, object B's energized state is interpreted as both a change in velocity and a change in mass. Observer A needs to mediate the fracture in its observed reality. Like the original cycle we constructed, the observer begins to move with object B. However, if observer A views itself again at rest with respect to object B, we can see a problem. Even though the primary observer has caught up to the co-observer, object B is still energized. Not only did its velocity change, but it increased in mass according to the Lorentz transformations. If observer A originally witnessed itself as at rest with respect to particle B, it must re-achieve that relationship to re-establish its reality. Even though they're at rest again, object B would still be unexplainably energized. To account for the dilation, the primary observer must continue to accelerate. So, what is really happening? To describe the gravitational field cycle, we will need to construct a diagram resembling our entropic expansion cycle diagram. At time t0, the primary observer witnesses the co-observer to be at rest relative to itself. Instantaneously, the primary observer observes the field. The tremendously fast push causes the primary observer to perceive a portion of the momentum increase as dilated mass. The rest of the momentum change is interpreted as an increase in the co-observer's velocity. As the primary observer accelerates toward the co-observer, it observes particle B to slow down. Eventually, the primary observer can compensate for the change in velocity of particle B. This, however, will not properly reconstruct the primary observer's reality. At the start of the field cycle, a portion of the field's unexplainable push is interpreted as a dilation in mass. To view the co-observer once again in its ground state, the primary observer must account for the co-observer's dilated mass. As the co-observer loses speed, it converts the mass gained by the field back into velocity. The primary observer accelerates toward particle B until particle B sheds all the mass it gained in the field. At this point, the observer no longer views object B as energized. As far as the observer is concerned, reality has been restored. As we stated earlier, God is in the machine. When analyzing a single observer in the scalar field, there seems to be little to no evidence of conservation during field cycles. To understand how an external observer would observe the system, we must analyze the two observers together, viewing their observations as a commutable pair. Each particle observes a unique process during the field cycle. However, these two observations are equal and opposite. It does not matter which particle we select as our primary observer. When we overlay the two different observations of the field cycle, we can see that the process of the combined system is entirely internal. Similar to what we saw with entropic expansion field cycles, viewing the dual observers together forms perfectly internal equal and opposite processes. There is no apparent change in mass or energy during the fracturing and rebuilding of reality to an external observer. Even though the system's energy does not change, there is a change in the state of the primary observer with relation to the co-observer. When we overlay the simultaneous dual observations, we can see that, like entropic expansion, the changes in the system are entirely internal. In the end, The primary observer is moving toward the co-observer, and the co-observer is moving toward the primary observer. It is an equal and opposite relationship. This internal balance between the two particles assures no observable changes in the system's properties as it undergoes cycles in the field. Because of this, to an external observer outside of the quantum realm, such as a human being, we can conclude that cycles in the field would be impossible for us to observe. So, what is it that we observe if we cannot witness the processes of field cycles? We can imagine individual field cycles at the end of the limit paradox. After each field cycle, the primary observer's reality is conserved. It is these instances of conservation that build what we humans consider reality. Our reality is a continuum constructed by discrete instances of conservation. These instances flash before us like the clips of a film reel. A field cycle is the smallest unit of time. The expansion rate of the boson field dictates the rate at which all field cycles progress. Because the field is a uniform continuum, its rate of expansion is constant throughout the universe. Regardless of where a system is or how fast it is moving, it will undergo cycles in the field at a rate determined by the scalar field. We can construct timelines to see how field cycles create trends. We can draw a boundary around the system of two particles. Starting at the time t0, we see that instantaneously reality is fractured. The system then undergoes a field cycle to reconstruct reality. We can see that the field cycle does not perfectly replicate the system's previous conditions. Despite this, the primary observer and any other external observer observe conservation. Resulting from an entropic expansion cycle, we can see a slight displacement between the two particles after each field cycle. Repeatedly, the system of particles undergoes cycles in the field. As cycles progress, the two particles become more and more displaced. Despite this displacement, we see no change in the internal state of the system. Now let's construct a timeline to record the cycles between two particles in the gravitational regime. Initially, we can view the system at the time t0. Instantaneously, reality is fractured. Reality is rebuilt. As cycles progress, we can see that each cycle produces a small velocity inward. Humans can only observe aggregations of field cycles. We observe particles continually gaining a discrete amount of velocity. The aggregation of these field cycles is what we call acceleration in a gravitational field.